Hello everyone, we are Team Aetherion Zenith and our project is VOMX, that is Versatile Yield-Oriented Modular Avionics, a reconfigurable physical validation platform for next-generation launch vehicle avionics. The main objective of our project is to provide a physical platform for validating launch vehicle avionics and GNC systems before moving to expensive and high-risk flight testing. Now let's see the proposed solution. Launch vehicle avionics require repeated physical validation under changing conditions. So, simulation can predict the vehicle response, but it cannot completely reproduce real-world effects such as sensor noise, actuator delays, thrust variations, and physical disturbances. Also, conducting repeated real flight tests is expensive and difficult. So, our proposed solution is VOMX, which is a low-cost and reconfigurable physical digital validation platform. That platform allows us to test different vehicle configurations, introduce sensor faults, actuator limitations, thrust variations, and external disturbances. The most important feature is the iterative cycle: test, analyze, modify, retest. This allows us to test an algorithm physically, compare the actual response with the simulation, identify the simulation to reality gap, modify the system, and test it again. Now let's see the technical approach. Coming to a technical approach, this is the physical configuration of our VOM landing. The CAD model consists of a cylindrical body, internal support plates, vertical structural members, a central propulsion system, and landing legs. We developed the design and 2D analysis using CATIA and ANSYS as shown in this slide. For the preliminary design, we considered an overall height of 610mm, body diameter of 180mm. The propulsion system uses a 12-inch, approximately 305mm propeller, and the TVC system is designed to withstand approximately plus or minus 10 degrees in pitch and yaw. So now I will explain the main calculations used to establish the feasibility of this design. First, we calculate the vehicle weight. The mass is 1.3 kilograms, so weight is equal to mg. Therefore, W is equal to 1.3 into 9.81, that is 12.75 newtons. So the vehicle requires 12.75 newtons just to hover. For a VTOL vehicle, hover thrust alone is not sufficient. We need additional thrust for control and landing. Therefore, we selected an approximately 2:1 thrust to weight ratio. So required thrust is equal to twice the actual weight thrust. So therefore, our selected target of 25 to 30 newtons satisfies the approximate 2:1 requirement. Now coming to TVC, when the thrust vector is tilted by an angle theta, the thrust is divided into vertical and horizontal components. The vertical component is TV is equal to T cos theta, and the horizontal component is DH is equal to T sin theta. At 25 newtons at 10 degrees, the vertical component is approximately 24.62 newtons. Similarly, the horizontal component is 4.34 newtons. For a 1.3 kilogram vehicle, this gives horizontal acceleration is equal to 4.34 or 1.3, which is approximately 3.34 meters per second square. So the TVC system provides horizontal control authority while maintaining most of the thrust in the vertical direction. Now, let us see the feasibility and viability. Coming to feasibility, the major components required for this platform are already commercially available and proven. These include BLDC motors, IMUs, flight controllers, ESCs, and TVC mechanisms. For the preliminary calculations support the feasibility of the prototype. For a 1.3 kilogram vehicle, our target of 25 to 30 newtons gives a thrust to weight ratio of approximately 1.96 to 2.35. Impact and benefits. The major benefit of VOMX is that it enables rapid physical validation of vehicles and GNC system before expensive higher fidelity testing. So this project has higher value. These are some of the research and references of our idea. That's all about our idea. Thank you.